Okay, good news, because I have two monitors. The craziness that my computer is doing isn't showing up in the video that's recording, but for me, the screen is vibrating unimaginably and it's barely legible. So if I get really dizzy, I apologize because it's really distracting. Okay, so we were talking about scientific notation. So that's where we try to take a big number, a small number, and write it with as few things as we can, just because they're so large, we're going to have so many numbers. And we talked about it's usually the by 10 to the power of to show how many places we're moving that decimal point. If you're in Excel, though, they'll often use the E here. So we'll use 5 to the exponent 6, so times 10 to the power of 6 for this example. So we've moved the decimal place 1, 2, 3, 4, 5, 6 spots over. Significant figures are a different thing. Significant figures is how many of the digits we're going to use that are going to carry meaning in our calculation. Some fields of science are very, very, very particular about this. So the idea here is that if we have a number that has a ton of decimal points after it, so pi, for example, we think of as 3.14, but it goes on and they've never found the end of pi. We don't want to have to write out all those numbers, and we don't need to for most of the stuff we're doing. Chemistry might need a few more significant figures than we do, but for us, 2 to 3 are probably going to be fine. I would probably tell you in a question, especially since we're doing so much of the testing stuff on Quarkus, how many digits you'd need after the decimal place, which is kind of giving you an idea of significant figures. But I'm not going to get too hung up on this, but you don't have to write out 30 points after the decimal place for these sort of things. So 5.2 pounds has 2 significant figures. 1.54 times 10 to the 4 has 3 significant figures, the 1, the 5, and the 4. 1,100 kilograms, it's not really clear. Are all 4 numbers part of it, or are only the ones part of it? So we know it's at least 2, but it could be 3 or 4. Like I said, typically 3 or 4 significant figures is going to be absolutely plenty in this course. So putting your number to the power of 10, there's your exponent button right there. Okay, let's go on and talk about triangles. We're going to do a lot of breaking triangles apart or breaking things down into their components on axial grids and then putting them back together. And to do that, having an understanding of basic trigonometry is very, very, very helpful. So there's 2 main things we're going to use in trig. One is Pythagorean's theorem. So here we have 3 sides of a triangle. We have the one side here and one side here. Let's call it O and let's call it A. And then we have the long side, or the hypotenuse. Pythagorean's theorem states that h squared equals O squared plus A squared. So O squared plus A squared equals H squared. But that means we can rearrange this. If we know any of the 2 sides, we can find out the third side. This is really handy for similar triangles. If we had a smaller triangle here, we knew these 3 sides, or any 2 of these sides, and only one of the smaller triangle, we could also use similar triangles. So look here, O is equal to the square root of h squared minus a squared. H squared is equal to the square root of a squared plus O squared. So if we know any 2 sides, we can figure out the third side. So let's talk about SOHCAHTOA. There's other names for it, but this is the one I've always learned. So this is using the relationships on a right angle triangle for sine, cosine, and tangent. So we have a right angle triangle. We have the angle of interest right here, and this is the opposite side. This is the hypotenuse. The hypotenuse side doesn't change. It's the long side. And then the adjacent side is the one adjacent to the angle. If we had switched and used this angle over here, the hypotenuse would remain the same. This would become O, the opposite side, and this would become A, the adjacent side. So if we know we have those 4 things, we only need to know 2 of them to figure out any other thing. And so this says the sine of the angle equals the opposite side divided by the hypotenuse. The cosine of the angle equals the adjacent side of the hypotenuse. And the tangent of the angle equals the opposite side divided by the adjacent side. So we only need to know any 2 of these things to figure out the other 2 things. So we can rearrange this if we wanted to know O. We know that we could rearrange sine to figure out that it's h times the sine of the angle. H would equal O divided by the sine of the angle. And if we wanted to know what the angle was, and we knew what O, or the opposite side, and H, the hypotenuse, was, the angle is the inverse of the sine of O divided by H. Now that is something you plug into your calculator. It is usually a second function right above your cosine, sine, and tangent. So if that's my sine button, right above it is going to be sine to the -1. So we can see that right here in the calculator. I'll show that in a second. Here is a big tip. Make sure your calculator is in degrees. Often I find people will do their calculations and they'll have a number that's almost right sometimes. And then if I plug it in, I'll see that they had it in degree or in radians instead of degrees. Gradients is a whole other thing, but make sure your calculator is in degrees when you're doing this. So here is just an example worked out where I showed a few things. If you had a few different pieces of information, these are great practice things. If you haven't done trig in a long time, go through and do these. Don't look at the answers, try it out yourself, and then figure out and then see how your answers compare to what I've shown you here. In later lectures, obviously I'll go through and do calculations for you, but this is just a review of basic trig, and I think you guys should have the skills to be able to go through and do this. Seems silly, but you need to know how to figure out things on a graph, because sometimes the points you're looking at aren't directly on the graph, or the ones that are obvious dots. So if we had this graph here plotting lengths and weights against each other, and we can see we have a series of dots plotted on here, and we wanted to know what the weight is for the length of something that is 5.4 meters long. Well, we would come over to where we think 5.4 is. We could get a ruler out if we wanted here. We want to get it as close as possible. We're going to draw a line up, and then we're going to draw the line back to see where that hits the weight. That looks to be about 30. That's pretty darn close to 30. So we'd say, looking at this graph, that W equaled 30 kilograms. So that's pretty good. It looks like the data was selected points, and then these looked like they were probably straight lines in between. Nobody actually calculated every little bit in between there. They calculated the main points and then drew a straight line in between them. And overall, it ends up looking a bit like a curve. We can do the same thing with a graph. We can actually get even a little bit more, or with a chart. We can even get a little more precise if we want. It's still just an estimate because we're straight lining between 2 data points. So again, we want to know what 5.4 is. And this is kind of similar to what we did on the graph. We'll come over between 5 and 6, and we know we want something in between here. So we know our answer should be somewhere between 25 and 36. We got 30 on the graph. Now, 5.4, I like to do this kind of thought check. Before I do the actual calculation, I like to know approximately what number I'm going to get. So I'd know right away if I had plugged something wrong into my calculator or got some crackpot number. 5.4 is closer to 5 than it is to 6, so my weight should be probably closer to 25 than it is to 36. I still don't know what the number is, but somewhere between 36 and 25, and probably closer to 25. Now, I've written out here how to do it. This sometimes takes a little bit of thought. On the next slide, I have a worked out version of it. But basically, we want to know what the difference between 36 and 25 is. We want to know what the difference of 6 and 5 is, and we want to know what that ratio is, and then we want to compare it to the difference between 5.4 and 5. Multiply it by that ratio we just figured out, and then we have to add back the 25 because we were figuring out something between 5 and 6. When we plug all that in, we get 29.4 kilograms. I know, this one's really abstract. Interpolation is something you get or you don't. But here it is worked out a little bit more. Essentially what we're doing is we're drawing the straight line between that 5 and 25 and that 6 and 36. So this is very similar to what we saw on the graph earlier, but we're just zooming in on that one little spot. And you can see we can draw a triangle here. This bottom part of the triangle is the 6 minus 5, or the 1. This part of the triangle is the 36 minus 25, or 11 meter. 11, that should be kilograms, and this should be, yeah, that should be kilograms, because this is meters here. Sorry, that should be kilograms. So we have these two triangles, and we can see that they're similar. So this length should be a similar ratio to these lengths. So we need to figure out what that ratio is. We have our 11 divided by 1 meter should be equal to whatever kilograms we need divided by the 0.4 meters, which is how far we are over here. And so when we do that, we get 4.4 meters. So this is over 4.4 meters. But we started at, kilograms. Sorry. I'm going to go back and fix this one for you guys. I clearly wrote this today trying to jam it in, thinking I'd clarify things because I normally do this on the screen for you guys. I'll go back and write this one clearer and re-upload the lecture for you guys. I'm off to a shaky start today. I'm sorry, and the fact that my screen is going absolutely bonkers isn't helping it. So I'll go back and fix all that for you guys, and you'll see what the hell I was talking about there. Okay, let's go on to units. These are just units you need to know. It's helpful if you want to have these written out and have them nearby for yourself. That would be pretty good. We're going to work a lot between metric and imperial. Most of the calculations we do are going to be in metric, but sometimes you're going to need to convert things over from imperial to do those calculations. It's good to remember that 1,000 millimeters is 1 meter, 1 inch is 25.4 millimeters, 12 inches is 1 foot. We're going to deal a lot with force and mass. 1 kilonewton, or kilonewtons, is a term we're going to work with a lot. 1 kilonewton is 1,000 newtons. 1 kilonewton is also 102.06 kilograms. That is also equal to 224.8085 pounds. 225 pounds is fine for most of the calculations we're going to do. We're going to deal with pressure. 1 MPa is 1 Newton per millimeter squared. So, 1 millimeter by 1 millimeter squared, it has 1 Newton on it. A Newton doesn't have much meaning to you yet. We're going to talk about that later in the term. 1 MPa is also 1,000 kPa. 1 kPa is 1 kilonewton per meter squared. So a 1 meter by 1 meter grid, we would have 1 kilonewton on it, would be 1 kPa. And we're going to definitely talk about that in great length later in the term. Moment. Moment is something some people have never heard of until we've started these lectures. But moment has the set of units kilonewton meters. Sometimes we have to work in things in kilonewton meters, and sometimes we have to work in things in Newton millimeters. The difference between those is a million. So 1 kilonewton meter is 1 million Newton millimeters. So we're going to have to convert back and forth between those sometimes. So the main point of today's lecture is strength, stiffness, and stability. Mostly we're going to look at pretty pictures today. And the best way to show you what these things are is to show you how they fail. So a lot of the pictures we're going to look at today is the failure of these things to work. It's our job to make sure these things do not happen. So we're going to talk about strength, which is the amount of load a structure can sustain prior to failure. So failure could be rupture, excessive permanent deformation, or buckling. Stiffness is the amount of force required to make a structure deflect by some fixed increment. And that's important because we want to make sure we don't damage the things attached to our structure. If we have a beam that sags down like this, and we have drywall on it, we want to make sure our drywall doesn't crack. And stability is the state of being stable. I know, absolute ridiculous statement, or the opposite of being unstable. Again, absolutely no help. Instability can be elastic, ponding, tipping, or sliding. I can tell you that you have an instinctive understanding of stability. Every time you take a step, you know how to stabilize yourself. Every time you pick something up, you know how to stabilize something. I like to tell my students that everything you need to know about structures, you actually already know. Everything I'm going to do is just going to confuse you all to heck, and then you're going to learn how to do all the math, and then I'm going to say, okay, now align everything you just learned back with your intuitive understanding of the system. Now, this is something I've always said, but now that I have small children, seeing especially stability is really interesting. Kids intuitively understand stability. When they play with Lego when they're really small, they build things that can't stand up and then they fall over. They get pretty upset and then they try again and again and again and again. And eventually they learn how to build something that's stable pretty easy. I guarantee you, if you sat down with a set of Lego, you would build something stable. And in fact, when you build your models for your studio classes, I always recommend to think about stability. If you have to stick it in too much styrofoam to make it work, it's probably not stable, unless you are going to do that concept in the ground to make it stable. If you need too much glue in a spot, that's a moment connection, which is a difficult thing to design. So you can usually tell by how you build the model where your trouble parts are in your actual structure. Now, these three things are things we have to check for every connection, every element, and every single system in a building. We do it again and again and again and again. And then we make a change. We have to go back and check all of those three things for all of those elements again. So remind yourself, strength, stiffness, and stability for every connection, every element, and every system in the building. So let's start with strength. Let's talk about strength for a few minutes. Strength, we used to design it in a very specific way. This is not the system we use anymore. I want to stress this. This is not the system we use. It's going to be in assignments. It's going to be in the final exam. This is a great question I have in the final exam, is what system we use. And I will put factor of safety in there, and it is wrong because it is not the system we use anymore. But factor of safety was a good way to design when we were first starting out doing design. What we say there is, so say we have a table, and we know that the table is made out of something and it has some capacity. We just know what the table is. We've tested it and we know at what load that table will fail. So now we're going to put a load on the table. Maybe I climb up on the table. And so Shannon gets up on the table, and that table is designed to perfectly carry a Shannon. One Shannon can get up on that table, and it is perfect. I go out, have lunch, have a cheeseburger and a beer, come back, get on that table, the table fails. Because it was perfectly designed to my weight. There was no buffer zone in there. So what we used to do is put in a buffer zone called the factor of safety. So we would say, okay, we want this table to hold one Shannon. We know Shannon weighs this amount. We're going to make sure we have a table that can hold some multiple of Shannon. Back in the day, we used to use a factor of safety somewhere between 3 and 6, depending on what type of thing we were doing. So let's say we had a factor of safety of 4 on this. So technically, we would design that table to be able to hold 4 Shannons, even though the ultimate goal was only to have 1 Shannon on it. That was our factor of safety. 4 Shannons is our factor of safety on 1 Shannon for that table. And doing that, we would make sure that we had a table that could resist those loads. Now, that was a great system. It worked really well. But what we've started to say is, well, what if Shannon had different things happening to her? Or what if the weight of the table could be changed? It doesn't look at anything about materiality. So what we've gone and done is changed the way we look at this problem. We've said, okay, we know what the load is on the system, and we can have different types of load. We will increase the load by some amount. Now, there are people who study statistics who have tested this and come up with what those increases in load are, or what percent we increase the load. And depending on the type of load it is, we might increase it by different amounts. The weight of the table itself is pretty exact. The table's not going to get bigger or smaller. We want to build in a buffer there anyway, so it might have a smaller increase than Shannon, because we don't know if Shannon's going to go out and have a cheeseburger and beer, or if she's going to go out and have a whole turkey dinner with all the fixings. So we want to build a different amount of buffer in for those two different loads that are going to be acting on the table. It's self-weight and Shannon climbing on top of it. And then what we're going to do is we're also going to reduce the capacity. We're going to figure out what capacity that thing has, and then we're going to say it's not actually that strong. So instead of just doing all of the modification on the load side, we do some of the modification or the being conservative on the capacity side. And what's really nice about that is that it lets us have different reductions in capacity depending on the material. Because some materials, we understand how they behave really, really well. Some materials, we might understand how they behave, but we can't be certain that they're as perfect as we need them to be. A good example is wood. Wood grows in the forest and has knots in it. It can have checks. It can dry at different rates, and that can all change the capacity of the wood. So we need to have different factors or reductions in capacity depending on the material type. So we're going to increase the load on the system, and we're going to decrease the capacity of the system. Or we could say we're going to factor the load and reduce the capacity. Because we're engineers, we like to give symbols to absolutely everything. If you see this symbol here, it often means it's talking about a load factor, or the amount we factor up a particular load. And this value alpha would be different for different types of load. Over here, we have a reduction factor for the capacity. So if you see this symbol, we're talking about how much we're going to reduce the capacity of that material. Again, to keep everyone on their toes, if you see a subscript F, it means we've already factored it. The reason this is handy is if you've done a bunch of calculations and you come to me and I'm finishing it up, I don't know if you've applied your load factor or not. Putting the little subscript F lets me know you've already factored it and I can work just with that load. If it doesn't have the subscript F, I'll know you haven't applied the load factor and I need to apply the load factor before I do any more work. Same thing on the other side over here with R for reduction factor, or the reduction capacity of it. So if you see a subscript R, you know someone has already reduced the capacity according to the code amount required. X here is just a placeholder. This is to represent that we could have P, V, M, T, or C. All those things don't mean anything to you yet, but they will by the end of this course. P is talking about axial loads in some abstract manner. T is talking about tension. C is talking about compression. V is talking about shear. And M is talking about moment. All things we're going to talk about in great depth. This method of design is called limit states design. Sometimes ultimate limit states design is what it'll be called. It is not ultimate state design. That is something completely different. That limit needs to be in there. Often you'll see me abbreviate ultimate limit states as ULS, and that's going to be really handy later when we talk about load combinations. So let's talk about the different types of load methods that act on an element. Most of you understand axial forces. You might not have called it axial forces, but you understand axial forces. That's compression or tension. So compression would be me trying to push in on my phone or pull out on my phone for compression or tension. Often compression will show us squashing the element, and tension is trying to elongate the member. Shear. Shear is a little bit hard to get our head around. Anyone who understands calculus probably gets it. What we're talking about here is what is happening on two planes relative to each other. It's about two planes slipping relative to each other. If I have these two pieces of paper and I do this, I am shearing them past each other. And we're talking about a single plane down an element. But when we're talking about shear of the object as a whole, we cut this plane right here. And then a micro fraction later, we do another plane. And then a micro fraction, another plane, and another plane, and another plane. Until eventually we get some accumulation of planes. And that's what you see in this drawing right here. You see these two arrows could have been put side by side right on this singular plane, but I'm showing it spread out a little bit to show you an accumulation of slip along a series of planes. And you can see it's making one side go down and one side go up. And we're getting this weird thing where a square starts to switch into a diamond. And that's going to be important again later in the term. Bending. Bending is where we start to get moment. When we say bending and moment, we're talking about bending moment. Oh, sorry, my kid is hurt. Okay, he's fine. I don't have to rush and pick him up. He just has a bump on his head. So bending moment is when we do something like this. Now, here's the interesting thing about bending moment. If you can see this side of the book is bound. This side isn't. So this would normally happen on both sides, but where one side's bound, it can't. As I bend this, look, do you see what's happening? These are slipping relative to each other. What we're trying to do is compress the top and elongate the bottom. I don't even think I have an eraser. This probably won't do it. But if you do it with an eraser, you can see it better. That we're squashing the top and stretching out the bottom when we try to bend something. That's going to be really interesting because that means we've actually got compression on the top and tension on the bottom. So technically it seems like we could rewrite this thing of moment, of something trying to bend this thing, as being two arrows trying to push this way and two arrows trying to pull out that way. So that is probably something that's going to be handy later on in the term as well. Torsion is one we're not really going to spend any time on. Torsion is trying to twist. If you've ever used a screwdriver, you have a concept of what torque is, or torsion. It's kind of funny because it's kind of a combination between shear and moment. It's written in kilonewton meters like moment is, but it has an aspect to it that is very similar to shear. You can see that we have this kind of triangular deformation happening simultaneously to the twist. So there is a relationship there between both moment and shear. But like I said, torsion's beyond the scope of this course. I just wanted you to hear it and understand that it exists. So strength, we can also have connections. So connections are where any two things come together. The seam of this book is the connection of all of the pages together. When we have a beam sitting on a column, that point right there is the connection point. And that needs to be designed as well. Not just the beam, not just the column, but also the connection between the two. So let's look at failures, because failures is always the fun thing to look at. Here we can see we have a compression failure. Now what's interesting about this is literally how we test the strength of concrete. When they are casting concrete anywhere, slabs, beams, columns, they have someone there taking samples of the concrete in a tube that looks similar to this. They take them back to the plant, store them on a shelf, and at 7 days and 28 days, they test them in a compression machine just like this. And they see what load these things squash before they pop apart. And when they squash, we know what the strength of that concrete is. And then we check and see if it meets what the design requirements were on the drawings. Concrete's kind of interesting because we don't know how strong it is until after we build it. Where steel, we know in the plant how strong it is. And wood, we have ways to gauge what the strength is before we build with it. But concrete, we have to be pretty darn certain we know how strong it's going to be when we cast that concrete. Because if we're wrong and it's not strong enough, we have to do a bunch of work. This is where I always get the question, what happens if it's not strong enough? Well, what we don't want to do is tell them to tear it out. That would be the absolute worst. But we can't have something not working. So what the engineer will often do is refine, and see if we can get away with that reduced capacity. If not, we might come up with a remediation method. Maybe we need another column somewhere. Maybe we need to do something over here. Or maybe we need extra reinforcement. Worst case scenario would be tear something out. And then just for comparison, here is a timber column in compression. Tension failure. Here you can see we have two samples. One has been stretched until it fails. Later on in the term, we're actually going to watch videos of this exact thing happening until we get our failure. Shear. So I said you probably understand shear in a plane. Here is two pieces of steel trying to slip past each other, and there is a bolt in between them. You can imagine that the bolt down here, the nut, the bolt head is here and the nut is up here, that the bolt itself must be on a diagonal like this. That's that slip plane that kind of goes on a diagonal that I talked about earlier. Where it really shows up is in a concrete beam. This kind of diagonal line here along our beam is the classic sign of shear failure. Bending failure is not going to look like this. This is a clear sign of a shear failure of a concrete. Here's another shear failure of concrete. So here you can see that this sheared off in this direction. This one's interesting that it sheared off in both directions. This is where I normally ask the class what they think might have caused these things, because one is only in one direction and the other is in both directions. So it's got to be something pushing the top and bottom relative to each other. So what loads would try to push a building over? Well, we've got wind and we've got earthquake. Well, if we have a really big, strong windstorm, we rarely get wind reversal. Yes, I understand that there are tornadoes, but they're very small, and we wouldn't often see such a clear diagonal failure due to a tornado in both directions, like this. Possibly a hurricane, but these look like they were pretty equivalent loads. And if you got one side of the hurricane going this way, you probably didn't get the other direction at the exact same intensity. So this looks like it was probably wind. It was going really strong in one direction and sheared the building in that direction. This one here was probably due to an earthquake, because an earthquake goes back and forth at almost the same intensity while it cycles back and forth. Shear failure is the most common method of slabs to fail. So you can see here that punching shear where the slab just slips down around the column. Often what we do right here is put capitals or drop slabs in a column. So if you've ever been in a parking garage and you've seen these kind of tapered cones or the zones of the concrete ceiling that's a rectangle or square that drops down a little bit, that is to reinforce the zone right around the column to limit punching shear, or shear where the slab slips down around the column. If you've ever stepped on a safety pin or a thumbtack, you have experienced punching shear, where the shear goes through the skin of your foot. It's the exact same concept. Bending failure. So here we have some bending failures. Here's a wood beam where we have two supports right here and load being applied right here in the center. And this got pushed down, bending the element so that it compressed at the top and stretched out at the bottom. It finally stretched out so much that these bottom fibers of the element failed. This is a concrete beam with reverse bending on it. So what you can't see in this is that the supports are way off the sides of the page in either direction. These are the loading points. So what they've done here is, so far I've always indicated something bending in this direction. For this, they've bent it in this direction. So they have supports over here somewhere, and they are pushing up on that beam. And as they're bending up, you can see we're getting a little bit of compression failure here, where the concrete is crushing. And then up here, where the concrete's trying to pull apart, because that side is in tension, we're getting cracks. Concrete is terrible in tension. It is so terrible that we pretend it has zero tension capacity. That's why we put steel inside our concrete elements. So we have reinforced, when we're talking about concrete, we're talking about reinforced concrete. And steel is amazing in tension. And so we put the steel in to take the tension load. So we, in this, would have put steel at the top. Remember, this beam is bending upside down from what we typically see. Here is a steel plate bending. You can see something interesting here. It gets a few cracks here, but it doesn't actually seem to fail apart. It eventually starts to bend more and more and more and more until it folds up on itself. That's because we have a few things happening here. We started with a bending failure, where we could see here. Then it started to yield, which is something we're going to talk about going forward. And then when it yielded, we ended up having large-scale permanent deformation, or serviceability, which could have turned into a stability problem. You can imagine if this was on supports here and here, and we put a load down on it, it would eventually bend so much that it would slip right off the supports, which would make it an instability problem. Here is a steel bolt being twisted until it had a torsion failure. Torsion failures are pretty easy to find, apparently, on the internet. So here's a steel shaft in a torsion failure. Here is a screw in a shear failure. You can imagine that we had two things side by side that shifted. This went down and that went up, and it has that diagonal. This went up and this went down. These two things wouldn't have been in the same connection, and we have that diagonal right there. Here's another connection failure where these bolts would have sheared off. Often what happens when they erect steel is they'll, you can imagine they're hoisting the steel in and they want to use that crane as fast as they can. They'll often just put one quick bolt in just to hold it in place so the crane can go off and do other work. And then somebody else comes back and finishes putting in all of the bolts in the system. In this particular example, it looks like maybe somebody didn't go back and put the bolts in before the system failed. Here we have a plate failing in tension. Not a common way for something to fail. You can see that it's been pulled apart until we actually have it cracked down the middle. So not a common way for steel to fail. Here's another connection failure. We have this column that's tipped over, and we can see that these anchor rods have pulled up out of the ground. Now, this is one of the places where I say everything you need to know about structural engineering you actually already know. If you were standing straight up and your friend came and pushed you on the shoulder, you would fall over. But intuitively, you would spread your feet apart and try to resist that load. So what we could do here on this column is take these anchor bolts and make them as far apart as possible. The further we get those apart from each other, the more it's like our feet spreading to resist that tipping load. We're going to talk about that mathematically later in the term, and we're going to give it a name on what that process is that you intuitively already understand. So let's talk about stiffness for a little bit. So we've already covered strength. Let's talk about stiffness. So stiffness is all about preservation of finishes. We can have vertical stiffness. We can have horizontal stiffness, vertical stiffness. We can have rotational stiffness. Our soil needs to be stiff enough to resist our loads, and we're going to talk about that when we talk about foundations. And we're also going to have vibration that we need to consider. So let's start with just kind of what the concept of what stiffness is. Stiffness is often represented by the symbol K, and flexibility is defined by the amount that a structure will deflect or rotate under a fixed amount of load. Flexibility is often represented by the symbol F. I'm not going to test you on this slide, don't worry, but I want you to understand that stiffness and flexibility are related. They're the inverse of each other, if you want to think of it that way. So when we're talking about how stiff something is, we're also talking about how flexible it is. And if something is too flexible and we've got other things attached to it, we could damage those finishes. So a building that moves too much that way, if it's full of windows, as we move, we could crush the glass and destroy all the windows. So we need to make sure that we have enough stiffness to not crack those windows. Drywall on a ceiling, same thing. So the guidelines for stiffness is often comfort. How do people feel when that thing moves? It can make you kind of nauseous if you're sitting on a floor, or even when you're in your home. I own an old kind of century home. Drop a marble on the floor and it rolls across the floor because we've got like 2 inches difference from around our house. A lot of that's due to settlement, but it's not very comfortable. Another reason is preservation of finishes, like I mentioned. So that would be a beam bending and we have drywall attached to it and we don't want the drywall to get destroyed. It can turn into a stability issue. We have drainage and we have interface with building elements. And so I'll go through all of these in a few minutes. Here is a table for serviceability guidelines. Now, these are set out in the code as guidelines. I don't want to say that you don't have to follow them because you would need a gosh darn good reason to not follow these guidelines. I've pulled these from each of the different material codes. So you can see here, each material has their own guidelines. And depending on what that thing is doing, there's different guidelines. And most members have 2 criteria that we need to look at. So here you can see we have live or snow on a roof with finishes susceptible to damage. So that would be something with drywall. If it's steel, it's the length divided by 360. If it's wood, it's the length divided by 240. For live or snow on a roof with finishes not susceptible to damage, it's the length of that member divided by, for steel, 300, concrete, 180, and wood, 180. And then we have the same criteria for floors with finishes without. And then we have roof or floor with dead and or snow loads. So for a wood beam, we would have to look at dead and live or dead and snow together, plus this other criteria that we need to apply. So we have 2 serviceability requirements we're often checking. These make great exam questions. So it's the length of the member divided by whatever is appropriate from this table to figure out what our serviceability limit is. So that would be in millimeters, how much that thing can move. So let's do an example. How much can a wood floor beam with drywall on it that spans 10 feet move? What is the maximum limit that we're allowed to let that move? Well, first we need to change our 10 feet into meters and millimeters, just because we're often going to work in that. You could do it in inches if you wanted, but we're going to work in millimeters for our deformation requirements or our limitations. So we would take the length and convert 10 feet into millimeters. So we would multiply 10 by 12 to get how many inches it is, and then multiply it by 25.4 to get how many millimeters it is. So we'll end up with 3,048 millimeters. The live delta criteria was for a wood beam with finishes that are susceptible to cracking, drywall is susceptible to cracking, is L divided by 360. So the allowable delta means change, so that's how much this beam can move, is the length, 3,048, divided by 360, or 8.47 millimeters. If we're talking about a cantilever, we have the criteria. So if we have something that is rigidly connected at the end, and we're going to see that it's drawn like that, we only have to use half of the deflection criteria, which means we can allow it to deflect more. But not really. If you drew this curvature, you can see where we're coming from. What we're really saying is that we're using half of the length of something. So basically for you though, if you see a cantilever, and we're going to talk about cantilevers going forward, so don't panic about that too much, it would be half of the criteria. So if it had been L over 360, we're going to use 180. Our buildings have a limit on how much they can rack as well. There's a few reasons for that. We don't want it to crush our windows. We also have window frames or shoes around our windows. If our building moves too much, our shoe moves and our window could pop out of the shoe. We also have to worry about the fact that there might be another building here adjacent to this building, and we could move until we actually bash into that building. So there's a few things that we're checking on this. The code sets out that your delta for wind is H over 500. So that's a pretty tight criteria. We're not allowed to move very much at all. You saw that live load deflection was L over 360. Now this applies story to story or over the height of the building as well. Earthquake, we let the buildings move a lot for earthquakes. It's H over 50 or H over 500, depending on very specific criteria. You don't need to worry about that. I'd tell you if we were doing anything with that. But the building can move a lot due to an earthquake, and we allow it to, because we're going to talk later about how sometimes that allows us to absorb energy as well. Vibration. So vibration is when things will move continuously. So we're not talking about a deformation that kind of sticks around for a while. We're talking about a really rapid vibration of something. One of the types of vibration we worry about is a continuous vibration. That would be a steady repeated load, like dancing or music. And what we don't want is our building to have the same vibration as the object, but we also don't want to annoy the people around us. So if I'm tap dancing on the second floor and you have an office building down the hall, that vibration of me tap dancing could transfer down the floor to the person in the office building or in the office portion of the floor. That would be really, really annoying. I know when I worked at Blackwell, there was some sports agency that was in the office next door to us, and they built a little basketball court in their office. And every Friday afternoon at 3 o'clock, they'd start playing basketball, which just meant there was absolutely no ability to work after that point. So we would all open beer instead. Humans often move at 2.5 hertz or multiples of that. I always tease my husband that his top and bottom parts of his body move at different frequencies because he kind of looks kind of funny when he walks sometimes. And so I always joke that he moves at 2 different frequencies simultaneously. I often at this point get all the students to stand up on their feet and raise themselves up as slow as they can, going up and down on their tippy toes. And going up and down as slow as you can is really hard on your calf muscles. And then I say, okay, now go as fast as you can. That is equally hard. And then I say, okay, go at whatever pace feels really comfortable to you. And people will start to move at about 2.5 hertz. It's the natural frequency that our body tends to like to move at, the things we do, or multiples of it. A transient load is when something bashes down and vibrates out. So we'll often do a heel drop to test vibration. And what we're hoping here is that the object has enough mass to dampen the load. So we go up on our tippy toes and drop our heels down as hard as we can and feel, and then we just stay still and feel how the vibration comes back up our legs. And what we're looking for is for that to taper off really, really, really quickly. And that means we've got good dampening on our building. We can have amplification, and you guys can look at some videos that I'm gonna show you about amplification. or a bridge collapse. This is sometimes called resonance as well. So what this is saying is that there's the natural, everything has a natural frequency. An object or a structure will also have a natural frequency. A bridge is a really good example. If you have something on the bridge moving at the same natural frequency, they can start to move together and amplify the load, and it starts to get bigger and bigger and bigger until we get really large movements that will eventually result in a failure. That would be the extreme case. If you've ever been walking on a bridge, a pedestrian bridge, while someone else is running on it, you feel their transient vibration and also a little bit of amplification, because the runner can start to get into a vibration with the bridge, and you can find it very discomforting. So all of these things are why we think about vibration. The rarity is that we're worried about failure. Mostly we're worried about comfort. And so we look at you stimulating the thing and causing vibration, but then we also look at someone else walking by you and causing vibration, and how does that make the people around them feel. So here are some images. This was my old crappy house that I lived in several years ago that I gutted and renovated from top to bottom. We had previously, this was a little dropped area, and this was a beam here that was hidden, and reasonably should have expected that to be a built-up beam. And we had in the attic put planks down and stored all of our stuff up there. We came to do the renovation of our little office pod right here and took off the drywall and saw that instead of a beam, which would have been a bunch of plies kind of laminated together, it was 1 2x4 on flat. So a fraction of the strength that it needed. Obviously, you can see that there is a massive amount of sag there, or vertical deformation. So we've got a very large movement happening there. Here is what it took to fix the problem. We jacked it up, and then when I calculated by code, we needed 3 2x8s laminated together. So before they had 1 2x4 like this, and now we have 3 2x8s like that. And we're going to see mathematically how having something on this edge versus this edge in bending is such an advantage. Here is a ceiling cracking due to excessive deformation. Here is brick having cracking due to excessive deformation. This one is differential settlement, where the soil is moving away from the foundation, or we're getting differential settlement due to the loads of the building. So soil can compress too. It's basically a big sponge. Some are stiffer than others. And what we need to make sure is that the stiffness is equal across the building. Even if it's strong enough, if this part moves down more than this part, we're going to have the building start to move differentially. Masonry is very unforgiving for cracking. So you can see here we have a massive crack in that. Here is a wall movement. So often our foundation wall will be like this, and we'll have soil piled up here, and it's trying to bend our wall in like that. If you've ever dug a hole in the sand and have a pesky brother or sister come and stand on the edge and all the sand kind of sloughs into the hole, that's the same idea what's happening here. You dig a big hole in the ground, and all the soil that's over here wants to fill in that hole. So we put our foundation walls in to resist it. In this particular case, it looks like they didn't put any rebar in. So when that wall bent, the masonry block had one side in compression and one side in tension. The compression side is doing okay. The tension side, because concrete and masonry do not like tension, is failing. Here is a lateral deformation. So all of our buildings need some sort of rigid system. Often you'll see cross bracing or a shear wall that tries to stop the building from moving. But in this one here, there's a series of tongue and groove planks that could slip relative to each other, and then a big opening. So after time, the wind just started to make that fail. So you can see that lateral deformations can ultimately result in an actual strength failure. So all of these things, strength, stiffness, and stability, can be tied together and lead into each other. So if you want, you can stop this video. In the page, you'll see that I shared with you a link to an article that has a video about the Taipei 101 tune mass damper. What I really like about this video, when you watch it, you'll see that there's a bunch of people in the top of a high-rise building that has a mass dampener, a tuned mass dampener, in the top of it to try to mitigate earthquake loads. And the idea there is that as the building moves like this, the tuned mass dampener moves opposite to it and lessens the impact of earthquake on the building. If you've ever taken a water glass and slid it along a counter, you've seen that effect happening. The water sloshes around and stops the glass from moving versus taking an empty glass and sliding it across the bar or the countertop. What's interesting is that the video camera is mounted to the building. So the building looks like it's staying still and only the tune mass dampener is moving. And so are the people, because people will naturally try to counteract the movement of the building. They are trying to actively stay upright, but because the building is moving and the camera's going along with it, the people look like they're moving because they're trying to counteract the movement. Except for one girl who's holding on to the building, and she looks like she is moving, the only one staying still, because unlike everyone else who's moving back and forth, she's the one actually moving more in space because she's holding on to the building. The other thing I suggest you watch is the Tacoma Bridge collapse. This was amplification of a vibration situation of a bridge. It was absolutely impressive in its failure. Wind came along and amplified the natural frequency. There was more going on. There was some things with the cables happening and a little bit of its kind of up and down vibration was, so there was, it's not just as straightforward as that, as nothing ever is, but it's a really good demonstration of vibration collapse. Very rare, like I said, but it is a good demonstration of vibration collapse. No people died in that bridge collapse, but there was one dog who unfortunately did perish, who was in the car remaining on the bridge, which is horrible and sad. The owner did not just abandon his dog. In spite of the movement of the bridge, he did try to go and save his dog, and the dog bit him. So he had no choice but to leave before the bridge collapsed, because it was going down, and it did go down, as you'll see in that video. Stability, the last little section I want to talk about. So stability is, like I said, the art of keeping something stable. You intuitively understand this. If you take a ladder and lean it against the wall, you know that you need to get it at the right angle to be stable. And you know that if you have it upright like this, it'll tip over. If you put it too far out, the bottom will slide out because it doesn't have enough friction resistance that it just kicks out and it slides out. You know, if you get it perfect, you always put a little bit of weight on it to see if you do have enough resistance for that friction force. So intuitively, you do understand some of these concepts. So let's talk about some of these stability issues. And remember, these stability issues can turn into serviceability problems, which can turn into strength problems. So they're all related, and it's not always obvious. You're gonna have a thought exercise in your assignment. And in that assignment, because it's on Quarkus and the way it can self-mark is by you putting the right answer in, what I really want you to do is think about it, and you'll get the final answers, so you can write yourself a note or something like that, and you'll get the final answers when the answers are available. But you're gonna have to put in the answer, I thought about this, or I thought hard, I think it tells you right in the question what to say. But the idea is there, I'm just trying to trigger you to think about this thing. It used to be a participation mark, but it's hard to, Quarkus doesn't really support a participation mark. Okay, so sliding, we have a force coming down, the ground is pushing up, and we have a force pushing on the side of the building. So we have friction stopping it and the ground pushing up as our reactions. We're going to talk more about reactions as well. If there's not enough friction to resist that force pushing on the building, our building is going to slide. Tipping We have the same things going on, but if we don't have enough weight acting on it, before it even slides, the building will just tip right over. Or if we have too narrow of a base, which is really the same thing. We can have elastic stability. We often call this P delta stability problems. What we're saying here is that everything kind of has a natural kind of imbalance or intolerance. So if we have a column like this, and it's out of plumb just a little bit, and we're putting a load on it, well, this causes it to want to bend just a little bit. And so it's in this position, and we analyze it, and we see how much it would move. But the load is still on it, and now the load is out further from center. So we say, okay, we're going to check that calculation again, and it's going to try to move it more. And we do that incrementally, and if the difference in the movement between each of the checks is getting smaller, we have something that's stable. If the difference is getting larger, we have something that is unstable, which is not what we want. We do not want an instability problem. So you'll hear engineers talk about the P delta effect. This is the P delta effect right here. We can also get the P delta effect in ponding on a roof. So you can imagine we have a roof with some water on it, and it's going to deflect just a little bit. Well, the water is going to redistribute a little bit so that more of the water is in this middle zone right here. So now we have more water in the middle where it wants to bend the most. So now it's going to deflect a bit more, or we'd calculate how much more it would deflect, and we'd see how much more it would move. Now we've got more water. And again, we do that to see if the difference between each of our checks starts to get smaller, or if the difference in movement between each of our checks gets bigger. If it gets bigger, it's unstable. If they get smaller, it's stable. Buckling is an instability problem. So that's when we're pushing on something in a compressive load. So here I have a piece of paper. If I try to crush that, it takes almost no force. It tries to buckle. If I do the same thing with the paper in this direction, I'm just pushing on paper. It's like I'm pushing my two hands together. Or if I did it, it's a little bit easier to see like this. We're not worried about buckling. So compression loads can be about strength, or we can be worried about how slender it is or how likely it is to buckle. We can have local buckling, which is saying that one small part of the object might buckle locally. And I'll show you pictures that differentiates between those two, because I often get a lot of questions where people don't understand the difference between buckling and local buckling. Buckling is when the object as a whole buckles. Local buckling is when one side of it or one element of it buckles, and then the whole thing starts to fail. So if the whole thing is buckling, then we've got buckling. If just one tiny little part of it is buckling, then we've got local buckling. Local buckling can turn into overall buckling, though. Tipping. It's not often that you see a building tip over, do you? But here we do have a stability problem with tipping. This happened while I was in my engineering career. It was kind of interesting because remember that digging a hole in the ground problem I talked about, and a pesky brother or sister standing on the hole trying to push the soil in? Well, this building, which was under construction, it wasn't occupied, thank goodness, they had dug a big hole for the next building beside this building. So we have a nice big hole right here, big building right here, and then they took all the soil they dug out of this hole and brought it over and piled it up really high right here. So all of this soil tried to push in the hole and took the building along with it. Everybody always gets obsessed with these little piers. The little piers were probably just fine for the gravity load and even the overturning of a normal system. This was a stability problem where the whole thing tipped over because the soil started to fail and then the whole thing failed. Sliding. It's really hard to find a sliding failure in a building. I don't even know what this is about. How a whole building just kind of plops there. Maybe it was a tornado. I don't know. I'm actually going to guess that this was a building on the back of a flatbed, but it actually looks like there's curtains in this building. So I'd be surprised if it was just being transported as a trailer building and slid off the back of the flatbed. So I don't know the story behind this, and we don't often do know the stories behind these failures, but I just wanted to show you what sliding might look like when the building as a whole kind of just shifts around. Ponding. Here's a demonstration of ponding started happening. So you can see that the water is pooling right here. This happens a lot where we put new mechanical units on existing buildings. So our buildings were working just fine. We put a heavy mechanical unit there, causes the building to deflect just a little bit more than we're used to. The next time it rains, the water tends to pool in that spot, which causes the roof to deflect a little bit more, which makes more of the water pool in that spot, which causes it to deflect a little more. And that can amplify again and again and again until we have an entire failure of the roof. Lateral torsional failures. So this is interesting. Remember I talked about buckling of our column, and that happens in compression. Well, buckling doesn't happen in tension. And when we have something in bending, the top is in compression and the bottom is in tension. So the top of an element in bending wants to compress, and it could be susceptible to buckling. But the bottom is in tension and it is not susceptible to buckling. So as the top buckles, it tips a little bit, and as it tips, it twists the whole object. So the top would compress and twist the whole thing over, and that's why we call it lateral torsional buckling. The top starts to buckle, and then it starts to twist sideways. So here's an image of a buckling failure. You can see both sides of this buckled together. Well, that same test is done with local buckling, and I'll show you that in a minute. When we were jacking our ceiling to put our new beam in, we used a steel post jack, but that doesn't have small scale movements. It only has large scale, several inches movements. So what we needed to do was jack it in increments and then put new pegs in as we raised this. When we got to the height we needed, we realized we were really close to buckling two 2x4s screwed together. The force that it takes to do that is really, really high, and we're going to talk about that later in the term. And what was really interesting is that it didn't take much force on our part. It just took this lever to turn that into a buckling force. But you can see here a buckling failure happened in this post. If any of you have taken the GO train and been late on a hot day versus a cold day, it's probably due to buckling of the rails. When the rails heat up, they tend to expand and they want to buckle, but they're held in place by the little ties. But it is precarious. And when the train goes over it, it can release those just a little bit, and the rails can pop loose and have large scale buckling. So that's why often on hot days they might have they might lower the speed requirements of a train to ensure that the track doesn't buckle. Here is local buckling in the top flange of a beam in compression. So you can see it's bending, the bottom is in tension, and the top is in compression. So we're getting local buckling here. Ultimately, this is being restrained from lateral torsional buckling because it's connected to this concrete right here. Here's another example of local buckling. You can see the top of this is all warped. And here's that same test. Instead of both sides being smooth and buckling sideways, this one here is kind of warped and bubbly. That's because this plate of steel buckled locally. So we're talking about a plate within the element buckling versus the object as a whole buckling when we're talking about local buckling failures. Here's just some big thin steel buckling. I have put up a video, or I've provided a link to Cast Connect's testing one of their high strength connectors. What's really cool is that it tests this, we see large scale bending, so we're going to see yielding, which is a strength issue, large scale deformations, which is a P delta serviceability issue. You're going to see yielding down here at the bottom. So it's all kinds of things until it ultimately has a rupture failure. So feel free to go and watch that video. And so the important things I want you to remember: when you're designing something in structures, we need to make sure that it is strong enough and stiff enough and that it is stable. And when it's strong enough, we need to do it for moment and shear and axial and tension. And then we have to do these things for every building, every element within the building, and every connection in the building. So strength, stiffness, stability, every building, every system, every element, every connection. And we have to check those things every single time. So today's takeaway tips: you should know where architects fit in, just for your ever knowledge, you should know where architects and engineers fit in the design process. You should be able to understand that there are different types of strength failures. You should be able to recognize a stiffness or a stability issue. You don't have to be perfect at it, but you should have an idea of how it works, which is why those questions in the assignment are participation, where you have to write in the answer that I tell you. For actual studying and going ahead in the course, math. If you're not comfortable with math, get comfortable with math. Find someone that can get you comfortable with those things I outlined for you. You should understand the different types of strength failures. You should be able to recognize a stiffness and stability problem. You should be able to calculate a factor of safety and a limit states design equation problem. You're right, I didn't give you any information there, but the equation is there. If you have a factor of safety, you factor up the load and it has to be less than the capacity. If it is a limit states design equation, you have to factor up the load and reduce the capacity and make sure that the capacity is greater than the reduced capacity is greater than the factored load. And then you should be able to calculate allowable deflections. So that's that chart where I showed you what the allowable serviceability requirements are based on the code. And you should be able to calculate those for varying lengths. You are definitely going to have that in the assignment. And for the undergrad class, you are definitely going to have that in the quiz. Okay, sorry for the few little videos. My computer is behaving in an absolutely horrid manner. I'm hoping it's not dying a sweet, slow death. Regardless, I now know that it doesn't have an impact on you and I don't have to pause and stop it. I apologize that I swore in the middle of that one video. Just ignore that. And next week we'll come back with fresh new videos. Okay, talk to you soon, guys.